All right, Nicole Buck is the PE Vice President and leads the Vermont office of North Star Hydro Incorporated, a private consulting firm specializing in hydrologic and hydraulic analysis for infrastructure applications. With degrees in civil engineering and geomorphology from Bucknell University and Dartmouth College, Ms. Buck aspires to improve interactions between the built and natural environments through careful study and design. Ms. Buck has specialized in hydrologic and hydraulic engineering related to transportation for the majority of her 20-plus year engineering career. Prior to joining North Star, Ms. Buck was research civil engineer at the U.S. Army Corps of Engineers, where she applied her graduate research modeling fundamental fluid dynamics and particle entrainment functions in both fluvial and aeolian environments. When Nicole is not thinking about floods and scours, she can be found clearing the Heartland Vermont School Board chairing the Heartland Vermont School Board, coaching ice hockey, or mountain biking in Vermont's wilderness with her kids, husband, and dogs. Awesome. Thanks, Nikki.
Okay. So I'm Nikki Buck, and we're going from the state of Texas to the tiny state of Vermont. And not only that, we're going to some small communities in the tiny state of Vermont. So I guess in some ways this is going to be quaint, but I'm hoping that I'm talking about the anticipation side of operational resilience. And so I'm kind of giving you some case studies from the state of Vermont from floods that occurred in 2011 that we're still dealing with the consequences of today. And trying to give you a heads up as to what may happen if you have a similar situation. So as an introduction, in Vermont, in 2011, Tropical Storm Irene dropped over 11 inches of rain in approximately 36 hours over the spine of the Green Mountains. Irene's legacy is an unprecedented volume of sediment, erosion, and deposition. Since then, some small rainfall events have caused broad infrastructure impacts in this region that I'm about to talk about. We use 2D modeling and geomorphic assessments to understand these regional flood patterns and understand how all of this is interacting with the infrastructure. And I'll be honest, we don't have the answers to how to fix all of this yet. This is a historical problem that started in the 1800s, and as many of you with older communities know, that these types of challenges are hard. So quickly, for those of you not from Vermont, you can see that Vermont is hilly. We have pretty large hills and then broad alluvial valleys. And so the Green Mountains run north to south along the center line of the state approximately. We have several water features, but two that I want to point out is you can see Lake Champlain up near Burlington. And then the Connecticut River is our border with New Hampshire on the eastern side of the state. The projects that I'm about to talk about are all those little red triangles just outside the Green Mountain National Forest. So just to take you back to 2011, which sets the stage for where we are now 11 years later. 2011 was a really wet year. By May of 2011, Lake Champlain, Vermont's largest lake, was a full foot over its previous record set in 1892. And the lake itself was 15% larger in area than normal. During that summer, 3 major rivers surpassed their 100-year flood elevations. And then we had Tropical Storm Irene. So then we had up to 11 inches dumped on the Green Mountains. So you guys can read all of the stats here. It was pretty devastating. The storm caused nearly $750 million in damage. And you can see here one of our primary east-west roadways is impassable. And just for reference, Vermont is a small state. $750 million is 2/3, in 2011, that was 2/3 of the general budget for that year. So this was huge. Again, we went from Texas to Vermont. So Irene, there's an article that was published in the Journal of Earth Surface Processes. I'm just going to read the quote because it kind of sums it up. Tropical Storm Irene in 2011 in the northeastern United States caused the most severe erosion of any flood in the historic record, surpassing that of great events with greater precipitation and peak discharges. So just a massive amount of sediment. Since so many of the roads are built next to rivers, again, historical communities, much of the damage was easily seen as you could see in the previous slide and the upper image here, and quickly addressed. But in other locations, as you can see here, we have an active railroad bridge where the low chord has been submerged since approximately more than 50% of the time since 2018. Here, we can't see what the damage was, and the damage is progressively getting worse. So here we're going to drill in from the big picture into our area of interest. These are two communities in southwestern Vermont, the town of Dorset and the town of Manchester, Vermont. Both are kind of bedroom vacation communities for New York City's wealthy residents. And you can see some of the pictures that I've gotten from one of the river management engineers in that area. There's a lot of sediment and a lot of flooding, and all of these pictures are from 2021. So this didn't happen back in 2011. This is progressively getting worse. So I'm gonna look at two case studies, but as you can see from the red dots, there's problems all over this region. So our first case study is Lye Brook in Manchester. As you can see on the eastern side, Lye Brook was bermed in the 1800s as part of a lumber operation, and the brook was confined to the eastern edge of the valley. The berms were selectively maintained until Vermont's stronger environmental regulations came in the 1980s, and they were no longer maintained because of the permitting requirements. In the late 2010s, around 2017-18, town officials and VTrans were frustrated by the number of frequent overtopping events for relatively minor storm events. You can see the road with the two dots on it, that's Richville Road, and it was frequently overtopping for 1.5 inches of rain, which is really not that big of a storm event. So we were hired to develop a 2D model using SRH-2D to investigate the adding additional culverts or doing selective improvements on the berm. So we built a 2D model, and let me see if I can get this to run. Okay. So we built a 2D model, and do I have a laser pointer? No. Okay. You can see here at the where the yellow arrows are. Lye Brook is running along the eastern. On the western side, you can see the Battenkill River. So at the two yellow arrows, Lye Brook is jumping out of its banks. This is for a 2-year event. So this river is really not functioning the way it should be. And then when you get down to the red arrows, you can see that for the 2-year event, it's flooding Richville Road, which is what the town officials are seeing. And then the lower red arrow is a historic property that's built in the 1800s. And this property is getting flooded, and the house is getting flooded for those really small, sometimes even annual events. So we got some problems here. So why is it out of its banks? You can see at the red line, I have a cross-section that runs from west to east. And on the right-hand side, you can see Lye Brook. You can also see the little tiny blip of the berm. And then you can see that the wetland channels are substantially below Lye Brook. So many of you maybe heard, if you took a geology class while you were in college, never build on an alluvial fan. And a lot of our communities are built on alluvial fans. So this is the prime example of don't build on an alluvial fan. Now we have a river that's collecting sediment that is above its wetland channels and no longer functional. So I validated the model. I walked the entire 1.5 mile length of Lye Brook. And you can see here, this is a normal low-flow October day, and the water is just pouring out the side of the berm. It's not even a storm. The water depth was a couple inches. So a significant amount of sediment that was really recent has entered the brook. And we could also see that by trees tend not to grow in rivers or near and under cobbles. So you can see that geomorphically. That was a relatively recent deposition. Again, we have a section of Lye Brook here. They were able to repair this berm after Hurricane Irene, but you can see that the brook is about 6 feet above the adjacent channel here. So we're buying time at this point. So just to sum up this case study, Liebrook didn't become perched as a direct result of Hurricane Irene. Like I said, we've developed in the 1800s on an alluvial fan. So we have 200 years of sediment. But Irene eroded and destabilized such a significant volume of sediment that has created a tipping point where this brook, which is about a half a mile away from the roads that it's impacting, is impacting those roads. And so historical development patterns and existing regulations kind of limit the solutions. And we're trying to find solutions. The most resilient solution, if I could change things, would be a planned divulsion and allow the river to take a new course and create a new bridge. But this is not something that's been normally talked about. For this project, it looks like after years of being dormant, it's going to come up again, and hopefully we'll be able to address some of those solutions. At the time that I did this project, the town manager was like, we can't add a culvert. I don't know what to do, and just shut down, and the project died. So it's coming back because the road's still flooding. So here's my second example up north. And so this is the town of East Dorset, again, a bedroom community of wealthy New York transplants. In East Dorset, thanks to some prior work from VTrans, we knew that the channel had become blocked, but we didn't know why or how to solve the problem. And again, our task when we were hired was to look at adding additional culverts or increasing the size of existing culverts. So here you can see here, we've got some substantial problems. If I start on the left, upper left side, we've got a residential road that's overtopping. And that road is a dead end, so when that road overtops, those residents are stuck. We have a historic restaurant that's continuously flooding, again, for minor events. We have another residential road that's overtopping. Where I flagged this here as an undersized culvert. This culvert was actually never intended to convey water. The culvert was put in as a cattle crossing when it was originally installed, and is now very much a water crossing. Back up to the right-hand side, we have a state-owned highway bridge, Route 7A, that has a really low freeboard right now. And you saw earlier, we've got the low chord of the railroad bridge that's submerged, and then that railroad is also overtopping. And this is an active railroad, so this is somewhat of a challenge. And these are just some images to show you some of our challenges. There's the restaurant, and the restaurant has seen a foot or more of water 4 times since 2019. And this restaurant didn't even really flood in 2011 when the hurricane hit. So this is all new. This is a new pattern. You can see the submerged railroad bridge, and it can't pass any debris because the low chord is submerged. You can see, again, going from Texas to Vermont, we have a lot of dirt roads. So this is our residential road, which may look more like a driveway to some of you, but it is a road. And it's overtopping pretty frequently. This is our state highway bridge, which on some days only has about 2 feet of freeboard with no storm conditions. And then again, we have another residential road that's overtopping frequently, and they had just installed a new culvert when that was intended. They've doubled the capacity of the road to convey water, and it's still overtopped, eroding some of the embankment. We did get one huge event since 2011, and that was the April 2019 storm, approximately a 15 to 20-year event. So this is just showing the flood conditions. This photo was taken standing on the highway bridge and looking at that railroad bridge in the distance. Again, wouldn't want to be standing on the railroad bridge right now. These are some imagery collected from VTrans inspection reports, and they were pulled together by VTrans. So you can see, starting in 2003, that's what it looked like, and that's how it functioned for the majority of its time. In 2009 and 2011, we still have a fair amount of freeboard. And again, these pictures are taken at different times a year, so there's some flexibility here. But by the time you get to 15, 17, and 19, you can see that there's something going on. So VTrans, understanding that there was something going on, hired aerial photography of the area. And you can see here, about 250 feet downstream of the railroad bridge, there's an active channel blockage. You can see the main stem of the river is blocked and gets progressively smaller. You can also see off to the left a secondary channel that's formed. So what's going on here and how, so we have to understand what's going on in order to solve the problem. So we developed a 2D model, again in SRH 2D, to look at the area. And so this is a spring storm. I'm guessing that this is approximately an annual event. And this was, we put in pressure transducers. So this is an actual event that we recorded and then modeled. And you can see here, you're getting substantial flooding in the wetland off to the right. But what's different in the last 5-6 years is that you're getting substantial flooding on the left, upstream of that highway bridge. So, and then you can also see that we're capturing the secondary channel in the 2D model. And then during lower flows, more water is going into the primary. Again, walking the model because it's important to see what your model is doing. This is an April, it's a regular day in April, non-storm event, but we are in snowmelt. So I was approximating that this is like the 50 to 75% annual flow. And you can see here that we have a lot of water flowing out into the secondary channel. As I walk out through the wetland, I can see a lot of water flowing in the wetland. And if you look at the lower picture off to the right-hand side, you can actually see that secondary channel. So it's a pretty significant channel that's formed. Again, I was able to drive on the limited access highway that you can see on the right, and I stood up on the limited access highway looking back on our project area. And you can see where those two blue triangles are, is the model predicting water flowing out of the main channel, and then I was able to visually see the water flowing out of the main channel into the wetland on that April day. I had to put the blue triangles up there because it's pretty far away and it's not as obvious when the sun's not rippling on the water. So what's going on and how do we work to solve these problems? I show here an image from October of 2011, which was flown 2 months after Hurricane Irene. You can see the blue arrow shows the direction of flow, and this is at that same location that I highlighted as a problem. That red line is a tree that came down naturally during Irene and partially blocked, was deposited in a way that it partially blocked some of the channel. Since then, that tree remains. So if you look at the picture on the right, you can see that red line highlights the tree, and then the tree caught another tree. And now we have the river being dammed by these two trees. Now these are all natural processes, and the geomorphologist in me says, great, you know, this is a natural process. We're shutting down the primary bat-and-kill channel, and we're allowing flow into the wetland, and this is what should normally happen in an alluvial environment. But this isn't helping our infrastructure at all, and it's making it pretty non-functional during some times. So what you can see here is that the blockage of these two trees, if you look at the post-Irene photo, you can see the channel is still pretty deep just based on the color. But since then, a significant amount of sediment, as you can see here in August of 21, the channel is not very deep at all, and it's not conveying the same amount of water as it would have. So again, we look at just to give you an idea of the loss of flow. The picture on the left is Route 7A, looking down towards the railroad bridge on a normal flow day. You can see it's a pretty wide river, still being blocked by the low chord, as you can see from the debris pile in the distance. But then if you look at the right-hand image, this is the main stem Bat-and-Kill River downstream of that blockage. It's about 4 feet wide, and it's traveling at a good clip, so it does have a higher velocity, but nowhere near the capacity to flow the way it should. So here we have a profile looking at channel thalweg elevations. You can see that we have a scour hole under Route 7 and another scour hole under the railroad bridge. And then when we go downstream, you can see that that tree is positioned approximately 1 foot below the railroad bridge. And this is the thalweg, so this is like the lowest part of the river. The average river, that tree, or that location is probably only 5 to 6 inches below the railroad bridge. So looking at this, it's not at all surprising that we're having major impacts to transportation. So, and one, I want to take a step back for a second. So it's like, well, duh, why didn't you go out and see this before? This is way back in a wetland, and there's some major bushwhacking involved. And I'll be honest, on the August day that I was able to get out there, this was one of the first times that anybody had actually set actual feet in this location. It was a steamy August day in Vermont, so there may have been some swimming involved, but we are not telling my insurance company that. So that is how we finally got out to this location to actually see what was happening. And then you can see downstream of the tree, the channel reverts back to its normal patterns. So what's going on and why are these sudden changes happening? And what I really believe is happening is that Hurricane Irene activated just a massive amount of sediment. And we saw that massive amount of sediment immediately following the hurricane and cleaned up what we could see. But in these rural areas, there's a lot we couldn't see. And all of that sediment is now active and it's working its way through. So any tiny little event is sending sediment down the stream. You can see the picture on the right is downstream of a bridge within the watershed, and there's so many cobbles deposited there that the river actually just disappears. The river is flowing through that cobble bed and no longer visible during low flow events. So that's the volume of sediment that's upstream. And then you can see from the April 2019 storm, we have some newly mobilized sediment, and that still may be related to the sediment activated from Irene, but I haven't been up to these sites yet to investigate. So this kind of gives you, once we figured out that we had this massive sediment deposit and we're trying to understand what was happening, we implemented a year-long monitoring program at the bridges. And so this shows the downstream face of the highway bridge, and you can see the low chord at the top. There was a railroad. They're actually in the final stages of redesigning the railroad bridge to be replaced. And so in 2019, they did a survey. So you can see the blue line at the bottom is the survey results from the 2019 railroad bridge survey. And then you can see by June of 2021, the volume of sediment that had been deposited in that location. Just unreal. When you stand up on the bridge, you're just looking at a pile of sand below, and there's really no functional channel. So then we had a scour event July 31st last year, and that high spot dropped about 1.5 feet. At the railroad bridge, it dropped significantly more because you could see that that is a tighter location. But it's starting to fill in again. So what we're seeing is that scour takes the finer material away, deposits it elsewhere, and then as soon as we get back to low flow conditions, that volume of sediment is just climbing right back up again. So what are the thoughts with this bat and kill project? The initial field evaluations showed that we had problems with a restaurant, some local roads, a highway bridge, and an active railroad. We used the 2D modeling and realized that adding culverts was not going to solve any solution. Like, we weren't going to find any solutions by just adding culverts here. The 2D hydraulic models really helped regulators and town officials who have no training in hydrology and hydraulics understand what was happening and visually see what we weren't seeing in our field. And right now, this project as NRCS is actively creating a design to remove that sediment blockage. But here's the ironic part. They haven't done the survey yet because the water is too deep and inaccessible to complete the survey safely. So that's in a bit of a holding pattern, but at least we have a solution here that will hopefully alleviate some of the challenges. So the big picture and why I decided to send in an abstract for this operational resiliency, in hydrology and hydraulics, we talk a lot about water. And I kind of wanted to stand up here and be like, but don't forget the sediment. During these big flooding events, and particularly with climate change, our previously stable geography may not be stable anymore because things have changed. And that's definitely the case here. And again, I'm a geomorphologist and a civil engineer, so I want to stand up here and say, don't forget about geomorphology, which I know that that's definitely a national program now, but this is kind of one of the examples of that. Historical development patterns are going to create challenges going forward. I think anybody that lives in a mountainous environment, I'm hoping that this is just a case study for taking it home and being like, well, adding culverts may not solve all of our problems on some of our highways. And then resilient design really needs to, should be based on the knowledge of how water interacts with the sediment and the physical landscape. So if it's coming out of a mountain, it's got high velocity, and it's going to take those cold cobbles and even sometimes boulders and suddenly cause them to interact with our infrastructure. I think that as we go forward, more and more conflicts are going to arise. And again, you can see here that, we thought we were done with Hurricane Irene back in 2013. We'll give us 2 years to have finished Hurricane Irene. And here we are now 11 years later and still dealing with this. And I'm going to go out on a limb and say that this sediment's probably going to be active for another 10, maybe even 20 years. So this is just going to be a continual problem. And then I have to put in a tagline for North Star. Our tagline is consider the water and how it flows. North Star going from Texas and FHWA to North Star Hydro. We're a two-person company. We're both trained in geomorphology and civil engineering. And our tagline is consider the water and how it flows, because we both feel very strongly that geomorphology and hydraulic engineering go hand in hand. And I have some time for questions. I'm going to hit on this. This is a picture, and the reason it's really bad is because it was we actually took a picture of a picture on the wall. But you can see off to the right, we have an active alluvial fan up there. And Route 7, which was that highway, that limited access highway that I was standing on top of to take a picture, has since cut right through that active alluvial fan. And in the 60s, you could see that that channel was going back and forth. And that channel no longer has that ability, or it has that ability, but the infrastructure may not like it when it switches. So just heads up. So I want to acknowledge everybody that helped on this presentation. My business partner, Ellen O'Brien, the Dorset town manager, Josh Carville, the river management engineer for this region, the Bennington County Regional Commission really stepped up and said, we've got problems here, we need to do something bigger. Ripple Natural Resources was also helping with the field work and design on this. And then VTrans for the back and forth that we've had and sharing their investigations. And then the Vermont rail system, because every time I went out to do anything, I had to call them and get permission to go out on the railroad. So there's a few references if you want to look at them later. And at that point, I'll take questions, but before I do, I have one of my field hands in there. And then this is the outlet of that alluvial fan, or this is where the alluvial fan starts. And you can see that the water is flowing off towards the left, but there's very little to stop it from going out to the right. So just food for thought. Any questions? Oh, we have a quiet audience. Oh, there's one.
Will those trees come out, the down trees? Is that part of the plan?
Yeah, it'll be woody debris removal and then also removing that massive sediment plug.
Could you repeat that question?
Oh, sorry. The question was, will the trees come out? In the image that I showed before where we have that, the blockage. Yes, the trees will come out and they'll remove the sediment. Any other questions? Yeah.
Yeah, I was just wondering what sort of response the railroads had, I assume if they're having issues.
Yeah.
What are their thoughts?
So, and I didn't get into all the details on this. The channel is actually, when it goes out of banks, it's using the railroad ditch as partially part of the primary channel. So that they're not super excited about that. And honestly, everybody's still trying to wrap their heads around everything that's going on here. a lot of people were blaming it on beavers. So the railroad just thought, we've got a huge beaver problem. We have a huge beaver problem. And yes, there is a beaver problem as well. But just this influx of sediment is causing the real havoc that we have right now. And again, in my dream world, taking off my geomorphology hat and putting on my engineer hat, I want to reroute this river, send it to the eastern side of the wetland, and let it flow where there's no infrastructure for it to damage. But then the geomorphologist in me says, no, that's not a natural thing. So put on the different hats. Any other questions? Okay, so those of you who live in mountainous environments, I hope that this provides a case study for just food for thought when you see challenges in your area. Thank you.